This circuit is a switch capacitor comparator, and it's a clever way to compare an input voltage, VIN, against a threshold voltage, VT high. It's a fundamental building block for the ADCs we are studying. The operation is split into two distinct steps, controlled by the two clock phases, phi1 and phi2, which you can see are non-overlapping. Let's first look at what happens during the phi1 phase, when the phi1 clock signal is high. The switches labeled phi1 in the circuit diagram will close. This connects our input voltage, VIN, to the left side of the capacitor CIF. At the same time, the other phi1 switch connects the right side of the capacitor, the node labeled VX, directly to ground. So, the capacitor CIF is charged up by the input voltage. The amount of charge stored, which we call QS, is simply the capacitance times the voltage across it, so QS equals CIF VIN. Think of this as the sampling phase. We've captured the input voltage as an amount of charge on the capacitor. Now, what happens when the clocks change and we enter the phi2 phase? All the phi1 switches open and the phi2 switches close. The left side of the capacitor is now disconnected from VIN and connected to the threshold voltage, VT high. The right side of the capacitor, node VX, is disconnected from ground and is now connected only to the input of the comparator. Here's the key principle, charge conservation. The charge that was stored on the capacitor's plates has nowhere to go. Because of this principle, the voltage at the comparator's input, Vx, must adjust. The slide shows that after the voltages settle, Vx becomes equal to VIN VT high. So, this circuit has ingeniously produced a voltage that represents the difference between our input and our threshold. Why is this so useful? Well, now the comparator has a much simpler job. Instead of needing to precisely compare VIN and VT high, it just needs to look at Vx and determine if it's positive or negative. If VIN is greater than VT high, then Vx will be a positive voltage. If VIN is less than VT high, then Vx will be a negative voltage. The comparator's own reference is essentially ground 0 volts, making the comparison very straightforward. Finally, notice the timing. The comparator makes its final decision and latches the output on the falling edge of the phi2 clock signal. This gives the voltages in the circuit the entire duration of the phi2 high phase to settle down, ensuring an accurate comparison. This single comparator structure is incredibly powerful. As we'll see on the next page, by creating an array of these, each with a slightly different threshold voltage, we can build a very fast and efficient flash analog-to-digital converter.